This question asks, which of the following alkynes will produce 2-butanone upon acid catalyzed hydration? There's a lot going on in this question. We have to think about naming and be able to draw 2-butanone. We're also told a specific reaction, acid catalyzed hydration. And so we want to think basically which of the following alkynes that we're provided with will be able to make the desired product. So we're going to kind of think through each alkyne and think through the products that it makes, and then we can kind of look at the answer choices. So the first molecule, if we were to treat it with the reagents that we need for acid catalyzed hydration, we've got H2SO4, H2O, and mercury sulfate. In this case, the key idea is that acid catalyzed hydration has Markovnikov addition. And so the enol that we would make in this instance would look like this. It's going to add to the more substituted position. And from here, we would make this ketone as kind of our final product. Okay, and again, we're looking for 2-butanone, and this does match up with 2-butanone. It's got the keto group at the 2 position, and it's a 4-carbon chain. So this is 2-butanone. So 1 will be able to make 2-butanone as a product. Let's take a look at option number 2. Option number 2 is an internal alkyne. Internal alkynes can undergo hydration reactions. It's just that the regiochemistry is not as important in this case because there's not like one carbon that's more substituted than another. So internal alkynes can undergo both acid catalyzed hydration and hydroboration oxidation. So in this case, when we add in our reagents, it doesn't really matter which carbon we add to. We could add to either one. And because this molecule is symmetrical like this, we can make the same enol from either side. I'm going to use another color here to show kind of the enol that we would make in this instance. Actually, let me put this in the right spot. It would be right here for the blue. And for the purple, we would have this one. And both of these will lead to the exact same ketone. And that is also 2-butanone. So molecule 2 is also capable of making 2-butanone as the product. In this instance, the internal alkyne makes the exact same ketone. That's not always the case. Again, internal alkynes can be like perfectly symmetrical like they are in this case, or they can be unsymmetrical. And an unsymmetrical internal alkyne would give you 2 different products. So that's something to keep in mind. Lastly, let's look at our final molecule. This one, just looking at it right away, I can tell from the starting material that it's going to be problematic, which means it won't make our product because it's got more carbons than we would need. Acid catalyzed hydration doesn't cleave carbon-carbon bonds, and so this molecule can't make like a 4-carbon ketone because it's got 5 carbons in it. We can think about what the product would be though, if we want to, just to kind of round out our analysis. This one will make this enol, again, adding to the more substituted side, but it'll give us 2-pentanone instead of 2-butanone. Okay, so 3 does not lead to the desired product. Now let's take a look at our answer choices. We have 1 only, 2 only, 3 only, 1 and 2, and then none of the alkynes. So we decided 1 and 2 would both work. And so that's going to be our answer for this question.